So hi. Today I want to talk about this really cool paper from Olivier Danvy and Meyer Goldberg, or at least I want to sort of start our journey with this paper because I think it is going to be a little bit of a journey. But at the beginning of the talk, before I say anything, I want to note that a really good programming language starts with three things. You've got primitives, you've got ways of combining them, and you've got ways of abstracting those combinations. And I think I'm going to be doing a little bit of each in this talk. And I want to make sure that that's all coming together nicely. So I invite questions. This room is really wide. I don't think you don't realize it when you're actually in the room, but wow, hi over there. So definitely feel free to raise your hand with questions in the middle of the talk, and I'll be happy to answer. So some of the pieces that we're going to talk about is we're going to take this paper, and the original paper was written in ML, but I'm a Haskeller, and ML is really cool for a lot of reasons. But today I want to translate that paper into Haskell, and in so doing, add some more types and show how we can use cleverer ways of thinking about equality to write cool programs that we wouldn't have otherwise been able to type check and prove them correct. And we'll also learn a little bit of grade school arithmetic in case you'd forgotten somewhere along the way. So the problem that we're going to start with is this one. So you've got two lists. They're of the same length. Doesn't matter what's in them. And you want to take those two lists and convolve them together, which means that you want to sort of take one list and so you'll notice that the first elements of this list of pairs that we get as a result are the elements of the original list. But the second element of each pair are the elements of the second list, but in reverse order. So that's to say that sort of as a specification by animation, we want to... Oh, hang on. My syntax highlighting needs to be higher contrast. There we go. Nice. Okay, so as a specification by animation, we want to spin one list around, match it up with the original list, and join them together into pairs. Now, those of you who like putting things together out of little bits of combinators would probably think, oh, well, that's really simple, right? You just zip one list with the reverse of the other, and you're done. All right, so I should just end this talk now, right? But there's another piece of the challenge problem that makes it a little bit more of a challenge problem, I would say. So we're given these two lists, and their lengths aren't known in advance, and we want to write a function that constructs this symbolic convolution in n recursive calls, that is to say with not spinning around forever, and with no auxiliary list. Well, I don't know about that. So you might think that we'd be able to fuse away this transformation, but actually we can't. So we actually do build up an auxiliary list. We take B's, we reverse it, we hold the entirety of B's in memory, and then we zip A's with B's. So we end up traversing the second list a full 2 times to do this convolution. And it would be cool if we could do it with just one traversal. So I want to present the solution from this paper, and I want to really give an intuition for how it works. And then I want to cement that intuition by adding more types. Now, I mean, sometimes you add more types, and it gets trickier to figure out what you're trying to do. But a lot of the time, the really good times, and I argue that should be most of the times, when you add more types, you can actually clarify what you're trying to figure out more. And so that's what I want to try to do, is get the type checker to work with us to understand exactly the structure of this really cool functional Perl. So the solution that Danvy and Goldberg give is this. And it's a lot longer than one line. So let's piece it together. We've got this auxiliary function walk that has two cases. When walk reaches the empty list, it hands us back the tuple of the empty list and y's. And when it reaches a const cell, it immediately calls itself on the tail and then does some transformation on the result of that recursive call. So right away we know that it's not tail recursive. And we're never going to be able to do this kind of thing tail recursively unless we translate the whole thing into continuation passing style, which we can do. But I feel like that's a little bit of an aside. Oops, I'm not completely on the screen. Right. Is that still visible for everyone? Cool. So I want to walk through how walk works. So notice that we immediately call walk on x's. That's the first argument of our convolution function. And we're starting with a stack, and I'm just sort of symbolically representing the stack of things that we have in our context as we're making these recursive calls. So we start with an empty stack, and we start with the initial list of x's. And then as we come down through this case, like we have walk of a's is case walk a's, and then walk a's is going to split, and we go down and down and down before we can do any of this. So we just sort of read the initial list until we hit the nil case. So our stack contains all of the elements that were originally in x's, but notably in reverse order. And we're going, because of course it's a stack. And we're going to make use of that in just a second. So when we hit the nil case, we hand back this, the tuple of the empty list and y's. And then we pop all the way back up the stack until we're done. And what we're doing in each one of those steps is that we take one of these tuples, that's r, comma, b const b's, and we give back the tuple a, the pair of a and b const onto r and b's. So it's sort of like slinkying two lists from hand to hand. We put one in the stack in reverse order, and then we slinky, as on the way back up, we sort of pour y's over from the right hand to the left hand, or rather from the left hand to the right hand if I'm showing you visually from your perspective. So what that looks like is, well, we take the first thing off the stack. That's going to be this a, which we're holding in our context, because after all, we made this recursive call. We take this a, and that a being xn, and we pair it up with y1. Well, we're still several levels of recursion deep. So next, we have to take xm off of our stack, a comma b const r. So we do that. Then we go all the way back up and get to here, where at the very end, we just pull out the r and hand it back to you. And there's your symbolic convolution. No auxiliary list, n recursive calls, and there it is. You'll note, if you're being persnickety, that I reversed which one I reversed. And that's because it was easier to present visually this way. But obviously you could swap the parameters and you'd be fine. So there's one thing about this definition. Can anyone guess by the title? So when I go to compile this, and I always compile things using fwarn and complete patterns because it's really useful. I get these two warnings that these pattern matches aren't exhaustive. Indeed, they aren't. So we can add in the error cases. These error cases are not explicitly acknowledged in the original paper, but they're noted in the text for sure. So say walk handed us back a non-empty list. Well, it could only do that because the b that we gave it was too long. That is to say that the number of times that we make a recursive call in walk is equal to the length of the list of x's. And so we pull that number of elements off of y's. So y's, if x's and y's are the same length, then walk should always give us back the empty list as the second argument when we call it at the top. But the types don't say that. And the same thing here, except in the inverse. The recursive call to walk should always hand us back a const cell, unless A is too long, which means that we made one too many or more, well, only one too many because we're going to throw an error immediately. We made one too many recursive calls to walk. But as I said, none of this is in the types. And Dunphy and Goldberg acknowledge this, saying that this definition induces a compiler warning about non-exhaustive pattern matching. But the warning is unfounded because the two input lists have the same length. That's a precondition, all right. I sure can call the function with lists of different lengths. And when I have preconditions, I like them to be in my types. So they go on to say that in a version of ML with dependent types, the type of the convolved taba function, I'm using taba to abbreviate there and back again, would be this, that for all n, where n is some natural number, and this is ML syntax. For those of you who are native Haskellers like me, to translate in your head, you swap the order of things. It takes in a list of length n of alphas, a list of length n of betas, and gives you back a list of length n of alphas and betas. And there's our precondition right there. So, but we're translating to Haskell after all. And in Haskell, that is to say, Haskell today, the type of convolved taba can be this. So, I just want to explain what's going on here with these lists indexed by numbers. We're going to need a bunch of language extensions, first of all. And especially, we're going to need this special module called ghc.typelets. So these type literals are a relatively recent feature of GHC that let you put actual numeric literals in your types and operations like addition and multiplication and subtraction over them. So the kind of 0, not the type of 0, the kind of 0 is nat. And the kind of vec is that it takes a nat and some type and gives us back a type of kind star. So for those of you who aren't familiar with GADTs and GADT pattern matching, although I think we talked a little bit about it in Stephanie's talk, I'm going to go over how to read this definition of vec, because these constructors are special. They're not just saying let nil give you back a vector of length 0. It's also saying, going the other direction, if I see a nil, then I know something more about the type index of the vector. That is to say, if I get a vec na where I have no idea what n is, and then I match on it, in the cases where I match on it, when I'm looking at nil, I know whether or not that vector has length 0. If I match on nil, then in that case, I can just assume that the vector has length 0 because that is in fact true. And that's the magic of Gadgets. So we can write a couple of functions over vectors. And I want to try, the idea here is I want to first build up the simple version that I showed you. The one-liner, zip of x's with reverse y's. And then after that, I want to build up what happens next, like how we can type check there and back again. But we're going to run into a problem. But not yet. Just wait. So we can zip two vectors together, and notice that the zip has indices here. So we're zipping together two vectors of the same length and getting back a vector of the same length out. And we don't have to handle the cases where things mismatch. GHC can figure out that if we match on nil for one vector, then that means that the other vector also has to be of length 0, which means that the other vector can only be constructed using the nil constructor, that this is a total pattern match in zip vec. And we say the zip of two empty vectors, or lists. It's strange that they're called vectors, but I'm using the established name for the type. is nil, and the zip of two conses is pair together the heads with the zip of the tails. And then we go to write reverse, and that's where all havoc breaks loose, because this doesn't type check. In particular, we get this kind of error message, where GHC says, well, a lot of things, but in particular, the important part of the error message, which I have excerpted for your reading enjoyment, is that it can't figure out that 1 plus x plus n is equal to x plus 1 plus n. So, borrowing a visualization from an earlier talk, we want to figure out that 1 plus x plus n is x plus 1 plus n. So how would we deduce this? Well, the first thing we need to do is we need to know that we can swap 1 and x. So let's do that by the commutativity of addition. And then we need to reassociate the left-hand tree to match it up with the right-hand tree. And so by the associativity of addition, we can do that. And then we've got the both left and right-hand sides matching each other perfectly. And so this is just true by the fact that our type equality is reflexive. So I didn't say this before. Twiddle or tilde is type equality. So that's to say that we're asking whether these numbers are equal as types. But GHC doesn't know that. GHC doesn't know that plus is commutative or that it's associative. Plus is just a type-level function that when you give it two ground types, two concrete numbers, can reduce them and find out that 2 plus 2 is 4. But it doesn't know that n plus m is equal to m plus n for all n and m. That kind of universal statement that we would need to rearrange when type variables are in play. And you could show GHC that plus is associative and commutative. And I want to go into what that would look like, because therein lies the rub. So, as we saw before in Stephanie's talk, we can construct this data type that witnesses a proof that A is equal to B. And so I've written it out a little bit differently, where we have this constraint here. And that's to sort of emphasize the fact that when we match on REFL, what we get out is that this constraint is true. If I give you an A equals B, and you say, okay, let me look at it, and you match on the proof, then inside that match on the proof, you get to assume that A equals B. So we can easily type check REFL at type 2 plus 2 equals 4. But if we try to type check REFL at 2 plus 2 equals 5, then we're not so happy. And neither is GHC, and that's wonderful. But then we can use proofs to discharge obligations that two things be equal. So this function with proof takes a proof that A equals B, and a thing that requires A be equal to B, R, and just gives us R. That is to say that there's no more constraint on R. This is sort of this is sort of like, or almost entirely like, modus ponens, except that is to say that the rule of implication that if we've got A and we've got A implies B, then we can just get A. We can just get B rather. We can also get A, but so. Except that there's two different kinds of arrows going on. We've got a proof of A equals B as a value, and then we've got an arrow that's a constraint, A equals B implies R. So, but otherwise it's just about the same. And we can use these tools to actually prove to GHC that plus has these properties that we want. But to do that, we need to use a different formulation of naturals. And don't worry, I'm going to pop the stack back up to using typelets. But I just want to take this diversion for a second. So using data kinds, we can define this kind of naturals. So that is to say that these constructors, Z and S, are going to be lifted up to the type level. And then we can define what it means to add them together. So 0 plus n is going to be equal to 0. Just checking to see if you're paying attention. And S of m plus n is going to be, so the successor of m plus n is going to be equal to the successor of m plus n. So we recur down on the left-hand side until we figure out in unary what the addition is. So we can build the same vec type except indexing by these naturals. And the reason why we can't use typelets is because the type level literals don't have the inductive structure that's necessary to actually show that this is going on. In particular, it has to do with the injectivity of constructors that GHC knows about, but it doesn't know about for type families. Ask me later if you have more questions about that. So using these pieces, we can put together some proofs where if I hand you a vec NA, and it doesn't care, I don't care what the A is, I'm just using vec instead of a singleton natural type because it's a little bit more convenient. We can prove that n plus z is equal to n. Well, it's obviously true if n equals 0, and we know that n equals 0 when we match on nil. And if we match on const, then if we can prove that n minus 1 plus z equals n minus 1, then GHC can figure out that n plus 0 equals n, just by reducing the type family just enough to get a toehold on what's going on there. But there's something going on here too. At runtime, there's something going on here, because these are functions. That is to say, when I give a vec to plus z, it actually matches down on the structure of the vec to produce this REFL term at runtime. And there's no way for me to get out the REFL without actually examining its structure all the way down to the tail. And the same thing with my distrib function that proves that m plus successor of n is equal to successor of m plus n. We actually have to tear apart the structure, the inductive structure of the thing we're working with, which should make sense because an inductive proof can be seen through another lens as being a recursive function. But we have to run those functions. And we have to run those functions for every number we want to find out whether these things are true about it, even though we know it's always true. So why do that? Why run proofs? Well, what happens if we don't run proofs? Undefined, after all, is of type A for all A. And, in fact, n plus z equals n is of type A for some A that is that. And n plus z equals z is also of type some A. So undefined inhabits all of these equality proofs, which means that if we don't actually examine equality proofs, if we don't force them and instead trust them, then we can get burned by any kind of non-termination that shows up in our programs. And that's a bummer. But we can still use this to put together a reverse vec that actually type checks. We can just plug in the proofs, and there we go. This type checks today with no real extra magic. But it's slow, and it's slow at runtime, like I was talking about. Every time that we prove that plus z is the case, that is, that n plus z equals n, for every n we want to prove that, we have to do effort. We have to expend effort proportional to the size of the number we want to prove it about. And the same thing goes for this distributive property that we wanted to prove, which means that our clever, efficient reverse that used an accumulator, this sort of like functional programming 101 kind of function, is now just as slow as the silly version that iterates down the list every time, throwing one piece of the list to the end. So we've lost the asymptotic efficiency that we tried to gain just because we had more types. And that's no fun. So instead, what we might want to do is tell GHC, oh, come on, you know how plus works. We don't have to prove it to you. And that's exactly what these type checker plugins that I said I would talk about and are sort of the core of this talk are about. So Yavor Diachky in the Haskell Symposium 2015, presented this really cool type checker plugin that means that when GHC gets stuck, it calls for help. Whenever we reach a constraint that GHC doesn't understand how to process, it calls out to this Z3 theorem prover through the bridge of the plugin to answer questions about arithmetic. And GHC and the plugin know that plus means plus. And so when we get stuck, we say, hey, does this equality hold? And Z3 knows that plus is associative and it's commutative, and Z3 knows a lot more things than that also. And the plugin says, hey, if Z3 said it's legit, I say it's legit. And GHC trusts the plugin. So yes, you could write a plugin that was totally unsound and said every type is equal to every other type. Don't do that. Or at least don't publish it. It might be a fun exercise. So then with this, we can type check the simple version of convolve. But I wanted to pop back up the stack, as it were, to type check this one with more types. So let's add in the vec type and say, okay, well, we know the type is going to be, it takes a vec NA and a vec NB and gives us a vec N pairs of A and B. We want to eliminate all those error cases, and I haven't written them in fact. All we need to do is to figure out, well, what's walk really doing? And remember how walk first iterates down its input, and then it goes back up, pulling things from the right-hand side to the left-hand side of this tuple. So we can fill in some numbers, and I want to justify why those numbers are right. In particular, when walk is called, so I've added, you'll note, a type variable m, which is the index of the vector that we pass in. So we know when we match on nil that m equals 0, and we hand back something of length 0 and something of length n. So that means that this is a pretty good guess, right? Because we're taking a vec ma, and we're giving back, I'll point over here, we're giving back a vec m a comma b. So that works in the first case. And then in the second case, we get back something from walk by this. If we apply this type inductively, we get back something of type m minus, or length m minus 1 and n minus m plus 1. And then we pull one thing, this one, over to the left-hand side to get m and n minus m. So the inductive argument just works. And the type checker plugin will gladly figure this out for us, provided that we annotate things. It can't infer that top-level signature. Although I just tried this with Liquid Haskell, which we'll be hearing about tomorrow. And Liquid Haskell can infer what's going on with the top-level signature. So that's really cool, and I don't actually know how it does it. And I want to ask Nikki, because it's really cool. So using the same pattern, and I want to illustrate what it looks like to use this pattern elsewhere, and how we can add more types to that. Some of the later examples in the There and Back Again paper, and there are more examples than the ones that I'll have time to present today. It's a really cool paper. We can find out whether or not something is a palindrome in only half the number of recursive calls as there are elements in the list that we're trying to find out whether it's a palindrome of. So how to read this definition? We're given, we pass initially the list and the list itself as the two arguments to walk. And walk steps down one of its arguments at double time, the second argument, and steps down the left-hand argument in single time. So that when we reach the end of its second argument, we're halfway, plus or minus 1, through the left-hand argument. And then as we pop back up the stack, we traverse the thing that we have yet to go down. That is to say, we're halfway through one of them, and the other thing, we've read the entire list into the stack. So on one hand, we're holding the stack full of the entire list, and on the other hand, we've got half the list in our left hand. So we walk down half the list, back up the stack from the other end, and check whether it's a palindrome by examining each pair of things using the same pattern. So we only have to go halfway down through the list in order to figure out what's going on. Of course, we're really going through the full list, but we're traversing the full list halfway up That is to say, we go halfway down on the way down, and we go the rest of the way down to the end of the list on the way up. So we use fewer recursive calls in order to compute this. And in fact, you can quarter this or eighth this just by using more auxiliary lists. And they say that you can also figure out whether something is a 3 palindrome, which is something that goes like a zigzag, like that. I don't have that on these slides. And the last thing I wanted to show, just to show like the kinds of neat magic that can show up with using type checker plugins. Notice, like, there's all sorts of inference happening here. We're figuring out that if we step down one list at double time, and then we get to a case where the second list is nil, or the second list is of size 1, then the original list must have been even or must have been odd. And we need to figure that out in order to type check the entire definition. And there are no annotations necessary on the recursive call. So we can also do something even fancier, perhaps, where instead of just returning a Boolean from our palindrome test, we convolve the two halves of a list together, where the list, of course, has to be of even length, of length 2 times n. We have to be able to unify whatever the length of the input list it is that we give it, and gives us back something of exactly half the length of pairs of elements. So we hand it, again, 2 copies of the input list, and we step down one of them at double time. And then on the way back, we pull something off of the second list, consing it together with the thing that we were holding on to in the stack. And you'll note the comment at the bottom. This won't type check with GHC 710 and with the current published version of Yavor's plugin. And for good reason, having to do with the fact that we only have type-level naturals in GHC, and we don't have type-level integers. And in order to figure out the argument that leads to this being type correct, you need to be able to instantiate things with integers. And there's a very, very hacked version of GHC which does type check this, but it also type checks some things that it shouldn't. So I'm working on it. But this is the world that I want to play in. So this is not the only thing that we might want type checker plugins for. It's just a really cool use case for type checker plugins. It's like, let's take this efficient version of the stack allocating rather than heap allocating version of a function and make sure that we can eliminate all the error cases by giving it cool types. So we might want other kinds of numbers. Integers, I mentioned, but also rationals, complex numbers, reals, who knows what else. And that means that we need some kind of a numeric hierarchy in the types that we're working with. Because otherwise it's just going to get a mess. And that sort of means something like, maybe we need type-level type classes. We'll see. And additionally, more complex data structures might be even more interesting to work with. And I know that I've already spoken to a lot of people who are extremely interested in doing things with type-level sets and maps. Not just functions that you can evaluate over sets and maps, but theories of sets and maps that we can use to figure out all sorts of things that aren't necessarily functionally determined. So we could implement something like row types with type-level sets and maps without having to have them built into the compiler. Just implement them as a library that has the right indices. But anything like that needs customizable error messages because the solver says no is just not good enough. And that's the state that we're in right now. We need better ways of figuring out why the solver said no. And that's something that I know is an active line of research both for me and for other people. And who knows what else, because there are lots of cool theories that we could integrate into the way that we type check. So in conclusion, what happens on the way up from a recursive call can often be more interesting than what happens on the way down. You're not just popping the stack, you're doing stuff. And that stuff can do more work than you might think it could. And adding rich types to programs that we're writing can teach us more if a sufficiently smart solver is working with us. We don't have to already know the answer. We don't already have to know the proof. We can collaborate with a smart solver to figure out exactly what's going on. There's also more than one way to know what's true. That if we're only reasoning with the tools that we have right now, that we're sort of bound within the boundaries of those tools. By plugging more complex notions of equality into the way that we type check our programs, and thus type check our brains, we can figure out more things about the structure of the programs that we're trying to write. So I'll conclude by saying, ask for what you want to know. Don't show it all. Don't prove it all. And go too slow. Thanks.
I'm certainly no expert in this area, but have you, and I know it's not always possible, but have you looked into ways to infer the extra information that you've provided in those types instead of having for me to actually explicitly work out the invariant, to just have the type checker tell me what it is after the fact?
Yes, and I'm still looking into it. There are lots of ways to get that kind of information. In general, arithmetic, nonlinear arithmetic is undecidable. So with sufficiently complicated numerical typed programs, you wouldn't be able to infer that kind of loop invariant. But we certainly would love to be able to infer simpler ones. And I think there's a lot of work to be done in that direction.
Because it seems like the compiler, a sufficiently advanced compiler, could infer the types that you showed today, but I don't know.
I think it's usually true that a sufficiently advanced compiler could. I'm working on it, and
right.
And I think it would be really cool if we could get rid of those annotations.
Maybe I missed it, but where did the times and minus come from? Are those type families that the plugin provides?
There are type families that type literals provides, and they actually do reduce on concrete ground literals. So if I can show you in the REPL. Hold on. Of course, this is subject to demo failure, but let's see.
But you're saying essentially GHC is providing them in typelets, because I only remember.
Right. So if I say, let's see. Oh, big enough? This is a very secret 8.0. This is my awful, terrible, no good branch of 8.0 that has integers that are called naturals. Don't tell anyone. So if I say, so 2 plus 2 actually does equal 4, and that will reduce.
So in your version with vectors, it ended up being quadratic at runtime. Mm-hmm. That was quadratic because of a parameter you had to pass in to make it, to evaluate a parameter that you passed in to make a type check.
Yes.
But so is there any chance of the compiler not getting it to optimize away the actual execution of that?
You would need to prove that the parameter you passed in was definitely not going to loop forever or be bottom.
Oh, that's why, okay.
And in general, that's not very decidable. But in specific cases, there are lots of ways of inferring totality, and in more conventional dependently typed languages, there is a totality checker, and you could imagine a system that, when it can infer totality, can erase those terms at runtime, if they're used only for equality. I would love to see that happen in GHC. I think it's a bit of a road to get there, though.
One more question.
So my question is, this is a lot of really cool type level stuff. Have you run this on any larger program? And if so, what are the compile times like?
Oh, that was the performance question I wasn't expecting to get. I have a prepared answer to the runtime performance question, but I'll answer yours. I have not. Z3 is quite fast, and
Does it do any kind of like caching at the type level where, okay, I've solved this before, just hand back the thing that I solved before?
Not between invocations of the compiler, but you could imagine a way of doing that. I know that Microsoft Research has a system for the Daphne programming language that caches verification results. But inside of a single run, it does use incremental solving for Z3. So that means that we save the state of the solver when we're trying to prove a hypothesis, rather than running the whole thing from the beginning all the time. So it's definitely smart enough to be not terribly slow. I can't say that I've type checked anything longer than maybe 50 lines, though, with no noticeable slowdown. I wanted to also answer the performance question. Would someone like to ask? So it is faster, and that's pretty cool.